And that's why there are diamonds in my backyard. Look, I see the YouTube stats. Nobody's watching it. I can say whatever I want. What was your question?
So you said a while ago that you weren't gonna, on the exam, like put like 4 different spectrum and we have to make the molecule from that.
Right.
So I always struggle with the ones where you give us like 1 spectrum and then like 10 molecules.
There won't be 10.
Okay.
All right, so the other thing, those worksheets, the type of problem will be similar. But, so again, I think if you look at old exams, like that rate where I had you like rank the 4 rates, on a lot of the old exams, it's just 2, like which one's faster.
Yeah.
That's the same problem. Like conceptually, it's the same stuff you got to know, but I get to that information quicker. The same thing is true in spectroscopy. You're probably going to see one where here's a spectrum, which on the worksheet it's which molecules fit it. My guess is I'll say it's going to be 1. It's going to be 1 molecule will fit this. And there's going to be like 4.
That's 1.
Right. So it goes faster. I mean, a timed exam just has to change. I kind of like the semester, and we'll see at the end. I'll try to make a determination as to which one I think works better. Like your final project that's worth 150 points is open note, open book. You could be working on it now. You actually know most of. There's only a couple of chapters really left that would be on that one. So you've got, you could be, not right now. You've got an exam Thursday. I get it, but Thursday night. You could start working on it. I don't want you not to have organic chemistry around, right? Like, people are leaving, like, screw that. So anyway, my point is, on a timed exam, it can't be as long. That's one reason I don't really like the problem where you come up with a molecule, because those can take, like if you see it, if you just immediately see it, but even when I don't immediately see it, it takes a little while to think through all.
So I was doing one of the old exams, and it had like which of these 2 are faster, and in one of them, it was like the only difference was the leaving group, and one was a BR and one was an OMS, and it like on your key it says that the one with the OMS is faster because it's a better leaving group. So I was just wondering where like OMS or like tosulates or like stuff like that like fit in comparison to like the
Yeah, they're definitely faster than bromides.
Okay.
And certainly way faster than chloride.
Okay.
They're actually usually a little faster than iodides.
So those are like the best leaving groups
Yeah.
then?
But I haven't gotten into that so much the last couple of years because it just seems like an unnecessary detail.
Does like a protonated like OH fall in that same category or no?
Yeah, actually, those are really good. The trouble is you can't use a protonated OH. So water can't be a leaving group with a good nucleophile or a strong base, because the water, it's the protonated OH is a strong acid. So any reasonable nucleophile is just going to take a proton rather than displace it. But yeah, actually, if you can make you can actually buy this molecule. Honestly, I have no idea how they make it. Here's a fun anion. Tetrafluoroborate. So you've got a B with 4 fluorines on it. You're not going to see that. Don't worry. But this cation reacts super fast with nucleophile. Like fast enough that if you get it wet, water just attacks the ethyl group and your reagent falls apart. So quaternary, if the leaving group is a neutral O that's got 2 bonds, that's a really good leaving group. But it's hard to use them in SN2 reactions. Yeah.
I have a question on the reaction on the left.
Huh?
Like, when you bring the CH3NH2 to the molecule, you like added the methyl group, right? For like the first time?
It comes with it.
Yeah, so like how come like the second or like this other time that the CH3NH2 attaches, like you don't bring another?
So this one, the thing that's attaching is not a CH3NH2. It's that nitrogen right there.
But for like on the right.
The red part?
Oh.
Yeah.
So like here, that methyl's coming here. So this proton goes from this nitrogen to that nitrogen.
Yeah, and then you attach the CH3, but like for the red part on like the bottom right.
Same thing, that methyl is attached to this nitrogen, so it's right there.
Oh, okay.
Yeah, so this is another kind of fundamental, so for all my jokes, this is a big one, now that two people have left, I'll tell you the skinny. Like when you look at a mechanism like this, so the nitrogen makes a bond to the H, there's an arrow there. The NH bond breaks, so there's an arrow there. There's no arrows anywhere else, so nothing happens there. If there's not an arrow to or from an atom in a mechanism, that atom doesn't change. So the mechanism directly accounts for every change that happens. So as you look at mechanisms you draw, and like I said, these are the first time you're going to have to draw one of these on an exam is Thursday, and there's a lot going on, right? There's not a simple, this is faster, or the product is this. The mechanism's got a lot of subtlety to it. But as you look at it, just make sure you've accounted, like going from this structure to that structure, make sure you've accounted. You've got an arrow to every atom whose bonding changes. And that no atom whose bonding stays the same has an arrow to it. Make sure your arrows kind of go in one direction, right? So you're all sort of going this way. It literally is a circuit. All right, so electrons start out on one end and they get dumped over here on this other end. And like I said, I would imagine if you take enough orgo exams, you will draw a really stupid mechanism at some point or another. You might, if you stay in organic long enough, you will publish really stupid mechanisms, all right? So there's a lot going on. Don't beat yourself up too much first go.
Can you explain how you determine the single versus the double arrows? Not yeah.
And then there's two,
No,
Oh.
The equilibrium
Yes.
or not.
oh, those arrows. Because getting into, but I'm going to answer your question. I love this. This arrow, everybody's like, it's just an arrow. It's not just an arrow. Each barb there is an electron. All right, so this guy over here, if that thing did something, it would be a single barbed arrow. We'll actually do some of that in the last bit of the class, okay? This is a much more meaningful question that you're asking. So single arrow, essentially I'm saying this is irreversible. Here I'm saying this is reversible. And it is, that's a hard call. The thing I often coach people to do, and this is like pure coaching, I don't know about teaching. If you're in doubt, put a reversible arrow in, right? So in theory, every chemical reaction is reversible. Now the difference is on this top one, okay, we're making a carbon-nitrogen bond, and we're kicking out an I minus. Let me actually put this, I'm going to draw this. Let's just put this one reaction up here. All right, so there's two ways to look at this reaction. One is through the base, or the nucleophile. Like if you think about it as a Lewis acid-base reaction, think back to Bronsted acid-base, right? The side that's got the weaker acids favored, also the side that's got the weaker base is favored. So here, if you just look at the base, I minus, so the pKa of the conjugate acid, pKa of HI is like -6. pKa of NH4 plus is about 10. Okay, so, and this takes, you gotta kind of keep track of this. The side with the weakest conjugate acid is the left. But you're not after the conjugate acid, you're after the base. And so base conjugate acid strength is inversely correlated. The stronger the conjugate acid, the weaker the base. Right? So what these pKa's tell you is I minus is a lot weaker a base than NH3 than ammonia. All right, or conversely, ammonia is a much stronger base than iodine. And you want the side with the weaker base to be favored. And so this is now like a 16 order of magnitude difference. So essentially, you can also get this if you go into bond, and you don't need to have bond energy tables memorized by any stretch. But if you go into, if you look at bond energies, the carbon-nitrogen bond is like 100 kilojoules per mole or so, kcals per mole, sorry. And the carbon-iodide bond is like 54. I mean, it's a huge difference. The carbon-nitrogen bond is much, much stronger. And so if you think about doing the reverse reaction would be iodide kicking out NH3. All right, so you'd be making a much weaker bond, and you'd be producing a much stronger base. So is that irreversible? Like in practice it is. If you mix these up, there is no going, if I take this compound and iodide, and in fact I could isolate that, it's going to be a white powder. I could put it in a bottle, it's not going to do anything. Again, you don't have to know that, but that's pretty irreversible. Whereas the second one that's got the reversible arrow, like I said, if you look at, so we got a neutral nitrogen and a quaternary protonated nitrogen. Down here we got a quaternary protonated nitrogen and a neutral nitrogen. Like really these two, they're not going to be exactly the same energy, but they're going to be really close. And so honestly, if you just mixed up one equivalent of this salt and one equivalent of amine, you would get roughly a 50-50 mix. You'd have like 25, 25, 25, and 25. The only thing that's driving this really is that you get to a second SN2 reaction. This again, the same thing is going on here. This SN2 is essentially irreversible. Strong base kicks out a weak base. So, like I admit, do you use an irreversible arrow or a reversible arrow and there's no hard and fast rule. Klein basically says 10 to 12 order of magnitude difference. Like an equilibrium constant of 10 to the 12 or 10 to the minus 12, you call that irreversible. But it's not like a law of the universe where if the equilibrium constant's a trillion, it's irreversible, and if it's less than a trillion, it's reversible. It's all kind of a spectrum. Like I said, here, this is essentially an equilibrium constant of 1 versus an equilibrium constant of 10 to the 16. So it's a big difference. Yep.
For the molecule that you had on the right before you erased it, if we had to draw the mechanism for that,
Yeah.
would it be concerted, like with the E2 and S2 happening at the same time?
No.
Or?
Yeah. That's a good enough question. I will redraw the molecule. All right, so we're going to have a hydroxide. You guys want to draw it like this because it's an exam and you're in a hurry, right? I guarantee if I asked this question on an exam, this exact question, I would see that mechanism a few times. And part of me would be really happy because the people who do this, the first time they ever draw a mechanism on an exam have drawn the correct E2 mechanism. Hydroxide grabs a proton, make a pi bond, kick out a leaving group all in one step. And they would have drawn a correct SN2 the first time. Nucleophile kicks out a leaving group all in one step. So the SN2 is concerted, the E2 is concerted. The problem with this mechanism is this is saying that all of this happens at the same time. And what that would require is this molecule to collide simultaneously in the right orientation with one hydroxide and then down here with another hydroxide, right? It's not the same hydroxide. So those two are actually separate. This would have to be two steps. And you could draw them either. I want to say the SN2 would happen first, but I couldn't take points off. If you drew the SN2 product, then drew the E2, then drew the E2 product, that would be a right answer. If you drew the E2 arrows and the E2 product, and then with that molecule, the SN2 arrows and the SN2 product, that'd be fine too. You could do E2 first, SN2 first. If you did this reaction and you followed it by NMR, you'd probably see some of both happen. Yeah, that's a really good question. So like I said, a mechanistic step, if I show all these arrows at once, then I'm saying all of this happens at exactly the same time. And reactions that involve 3 molecules in a single step are really, really rare. Almost every reaction you ever see that involves 3 or more products, or 3 or more reagents, those reagents come in stepwise, right? A plus B gives C, and then C reacts with D, or something like that. That actually having 3 molecules collide precisely at the same time is asking even a lot of a huge sample size. All right, that's 145. If you got anything else, I'll stick around for another few minutes if you want. You don't have lab today, right? That's yesterday.
So you know E2 is slow for leaving Greek bonded to sp2. Like, if we see that on the exam, so we just assume like.
I probably wouldn't say it. It really does depend. Like to do one of those in practice takes extremely strong bases or extremely high temperature.
Okay.
So when you see this in Orgo 2, or well, when we see this, I don't do much with it because of this reason.
Yeah.
We're going to do a chapter on making alkynes, and that's one of the ways to make an alkyne is to do this elimination from a vinyl halide.
And can we lose points for doing the irreversible, reversible arrows wrong?
Yeah, you can.
Okay.
Yeah. Kind of comes down to mood. It doesn't really. Hang Patty, hang on. It depends if you show me something that is really clearly like this is obvious this should be irreversible, or if it's something that really clearly should be reversible. On these first, I probably would be more likely to correct it than take points off.
And where's the link to the sign up for the Wednesday?
It's on the same sign up. I shared it with you a long time ago.
Okay. And I'm gonna be coming from a Spanish exam again right before, so I should be fine.
Yeah.
Okay, yeah.
You okay?
Yeah, it's my eyes. If you look at the inner corner, it's like not normal.
Yeah.
So I'm taking eye drops,
Okay.
but I don't know, we'll see what happens. I haven't really noticed anything, but
Well, I hadn't heard back from
Yeah,
him, so
sorry,
I was
thanks
glad.
for
No,
asking.
I was glad to see you in class. I was like, good, all right.
yeah.
So it must be. I think I've got like 9 or 10 in quarantine right now. So it must be
For
everyone in the other section,
Yeah.
because you guys seem. Like I know one of the people who wasn't here today. He was not supposed to be here. So.
Yeah.
Anyway, good.
Alright,
Well,
thank you so much.
Yeah, you bet. I'll see y'all.
Oh, so for the Wednesday review, it doesn't have the date on top, so I didn't put my name down because I didn't know, like,
Go in there.
does that count?
Put the
Okay.
date. Yeah. Sorry. Yeah, you guys should feel free to put the dates in if you want. Yeah. You got a question?
Yes, we had a couple quick questions about the worksheet,
Yeah.
the spec worksheet. So first for this molecule,
Mm-hmm.
this hydrogen apparently has a higher strength than this one,
Yeah.
but we were confused why. Is it just like some sort of interaction with that oxygen?
It's kind of an interaction with the oxygen, but not in the way. It's not a direct line like that. So. If you draw a resonance, the carbonyl pulls electron density from that carbon better than that carbon because of the way the pi bonds overlap. Right? So there's a resonance structure where the carbon that this proton's bonded to is actually got a full positive charge. So the electron density is lower and that moves it downfield.
Okay. Okay, that makes
Yeah.
sense.
Yeah, and so you could get that either from, you could get that just from thinking about the couple, or from the resonance or the splitting pattern. Oh, yeah, this is where you sketched it. You'd be fine. Like,
Okay.
yeah. I wouldn't, yeah, I can't imagine on an exam I would get too bothered by that. Probably like on the final project, and I can't now remember if I asked a question like that on the final project. I probably would expect you guys by then to be able to figure it out.
Okay.
But yeah, you're fine there. And what did you say on this one? I was curious what people said when I went back to work this.
For this one,
Yeah,
we said these two.
that's actually the one, and then that one would work too.
Okay. That was our other question about what the difference would be between cis
You
and
could
trans.
actually work it out, and I didn't go into it. Given the information I've included, you couldn't work it out. But if you look at the coupling constant, you see how these two are spread about the same?
Mhm.
That gives you cis and trans. So the two trans protons will split each other more than two cis protons, like twice as much. And so you can work out cis and trans by proton NMR. I just haven't told you guys how. So
Okay, so by looking at like the width between the two lines,
Yeah.
that would tell you.
Yeah.
And trans is,
trans is larger than cis.
okay. So it would be both of these from, given what we know.
Yeah.
we would sort of have a
And that
difference.
one as well.
And
I just wasn't sure. So that proton and that proton? So cleverly, I didn't write a key. If you guys ever become teachers of any sort, when you write an assignment, write the, like, as you're writing the assignment, write the key. Because I had to sit down and be like, okay. These two protons, I think, should have, like, that should be a doublet, or that should either be a triplet or a doublet of doublets. Same thing for that one. Like, they're neighbors of each other. And apparently they don't split each other. Because like on the spectrum, they're both doublets. And they have two neighbors. So like if anybody had said like none of these fit, I'd be okay with it. I would be fine. I could see their point. But yeah, if you got these two out of it, you're good. You should be in good shape.
And then for that complex splitting,
Mhm.
I know like you talked about it one day, like yeah, the doublet of doublets and that sort of thing.
Yeah.
But are we supposed to know like that? for this?
You will not have to use it.
Okay.
It might show up, but you'll be able to solve the problem other ways.
Okay.
So it basically just means, so splitting is an effect of one magnetic field on the observed magnetic field of another magnet. And so the n+1 rule says all the neighbors have exactly the same effect. But they don't. Sometimes one neighbor is gonna have a much larger effect than the other. And that one, like if I have one neighbor with a huge effect and two neighbors with small effects, the huge effect neighbor splits it into a doublet. And the two smaller ones would split each of those lines into triplets. So what it means is it's got neighbors, but they're different.
Okay.
And so that's probably enough to use. Like I said, I will not set up a problem that you have to use that to figure it out.
Is there anything else? I need to go through like the keys again. Do you have office hours today too?
I do, yeah. I'll be in the office some this
Okay.
afternoon.
Just 'cause I used to like go through the keys and check my answers again.
Yeah.
But I know, I definitely thought I could think on like.
Sounds good, yeah.
sorry.
And I'll so like where we were this morning, my plan had been to go sit out there. I actually have some stuff I gotta turn in to colleagues. So I was like, people haven't come to my morning office hours, so I'm like, I'm gonna stay in my office unless anybody says something. But if you come to Salem, if you wanna ask in person, I would come out and talk to you, and I might even just be out.
Thank you.
You bet, see ya. Hey,